Welcome to AI Paper Podcast, where we break down the latest research so you can stay ahead of the curve. Today we're tackling a really interesting one, the Markovian Thinker. It introduces this new environment called Delethink, and honestly, it looks like it could be a game changer for making long chain of thought reasoning. Well, actually practical. If you've worked with these LongCoT models, you know the nightmare. Standard RL training hits this wall, this fundamental compute cost issue.
Oh yeah, it's quadratic. The state, the prompt plus everything the model generates just keeps growing.
Definitely. So if you need, say, 100,000 tokens of reasoning, the cost just explodes. It's ON sauce, and that's it's basically unusable for really deep thinking.
It's a resource black hole.
Okay, so here's the quick version, the 1-minute takeaway. This paper proposes Markovian thinking, the big idea. Decouple how long the model thinks from how much context it actually sees at any one time.
And the way they do it is with Delethink. It breaks reasoning down into these fixed chunks, maybe like 8K tokens.
Right. And this forces the model through RL to learn to write this little summary, this textual carryover state at the end of each chunk, just enough to keep the thought process going after the context gets reset.
And the result, bam, linear compute cost, constant memory.
Get this, what they estimate costs 27 H100 months using standard LongCoT-RL. Delethink brings it down to just 7 H100 months.
That's huge.
It really is. It means we can potentially train models to reason for way, way longer than we ever thought feasible. A 4-fold saving is not trivial.
No, definitely not.
So let's unpack that standard approach first.
Sure.
Why exactly is it so painfully expensive?
Well, it comes down to the transformer architecture, really, and how we usually set up the RL problem. Like you said, the state for the policy, the AI agent, is everything the initial prompt and every single token generated up to that point.
The whole history.
The whole history. And for transformers, with their attention mechanism, processing that state means looking at all pairs of tokens.
So as the history gets longer,
the computation goes up with n squared. So generating the 100,000th token is vastly more expensive than generating the 10th. It compounds.
And people have tried fixes, right? Like multi-stage training or adding penalties for thinking too long.
Yeah, regularization, pruning, early exits, lots of attempts. But they were all fundamentally just trying to manage that quadratic cost when it inevitably happened on long tasks. They didn't eliminate the root cause.
They were band-aids on a scaling problem.
And pretty much. These researchers basically asked, okay, what if we change the environment itself so this quadratic scaling just can't happen?
Which brings us to the Markovian Thinker idea. It's about forcing the model to operate differently.
Exactly. Make it condition its next step only on a state that's always the same size, constant size. Doesn't matter if it's thought for 10 tokens or 10 million.
And Delethink is the machinery that enforces this. How does that work mechanically?
So imagine the reasoning process is chopped into these fixed blocks. Let's stick with 8K tokens for the chunk size, CN. Within that 8K chunk, the model thinks like normal, writes out its reasoning steps.
Business as usual.
But when it hits that 8K token boundary, poof, the environment wipes the slate clean, resets the context.
Whoa, okay, so how does it continue the thought?
That's the clever part. The new prompt isn't just blank. It's the original query plus a small bit from the end of the last chunk, maybe the last 4K tokens, if the chunk was 8K. This is the carryover.
So the model has to learn, through the reinforcement learning reward, to pack everything important into those last few tokens of the chunk.
Precisely. It has to learn to write its own concise summary, its own state update, knowing the rest will be forgotten. Ruthless self-summarization.
That's really smart, because now the model only ever sees a context of size C, or maybe C plus the carryover size, which is still constant.
Right. The state size n is capped at OC. It never grows with the total reasoning length.
So the math changes completely. The quadratic cost is only ever OCA, which is constant because C is fixed.
Exactly. So if your total thinking takes S chunks, the total cost scales, like OCOS. It's linear in the number of chunks S.
Compared to the old way, which was effectively O and chunk OS because the chunk size itself was growing with S.
That's the core of the efficiency gain. That's where the 27 months down to 7 months comes from.
Let's talk more about those resource benefits. The compute cost is one thing, but what about memory, especially the KV cache?
Oh, the KV cache is a huge one. In standard LongCoT, as the model generates more tokens, that cache of keys and values for the attention mechanism just grows linearly.
Right.
A 1,000,000 token trace. That cache could easily swamp a whole high-end GPU like an H100. It kills your ability to run multiple requests in parallel, your batch-sized tanks.
It becomes the bottleneck.
Absolutely. But with Delethink, because you reset the context every C tokens.
The KV cache size stays constant too. It's only ever proportional to C.
Exactly. Constant KV cache usage. Which means your throughput, how many tokens you can process per second, also stays constant no matter how long the reasoning trace gets. LongCoT throughput collapses over time. Delethink stays flat.
That's a massive operational advantage.
Huge. Though, there is a small trade-off, a crossover point they mention.
Oh, what's that?
For relatively short reasoning, say under maybe 30,000 tokens total, Delethink can actually be a tiny bit slower.
Slower? How come?
Because of that carryover mechanism. Tokens near the end of one chunk get processed as output, and then they're immediately reprocessed as input in the next chunk's prompt.
Ah, so you're processing some tokens twice, double cost for the non-attention parts of the network.
Right. For short traces, that small overhead might be noticeable. But as soon as the reasoning gets longer, like beyond 30K tokens, the ON cost of attention in LongCoT just completely dominates.
So the initial slight slowness is dwarfed by the exponential speed-up on longer tasks.
Precisely. It confirms their theory about where the quadratic cost really bites.
Okay, efficiency is great, but does it actually perform? What about the quality of the reasoning? They tested this, right?
They did. They used a model called R1 Distill 1.5b, trained on a tough math dataset, DeepScaler, and they compared Delethink, using those 8K chunks, against standard LongCoT-RL. On benchmarks like AME 24, HMMT 25, these are serious math competition problems. Delethink actually matched and even slightly surpassed the LongCoT performance, even when both were trained with the same total token budget, like 24K tokens.
Wow, so same or better results, but using way fewer resources per step because of the fixed context?
Exactly. But the really wild part was the test time scaling.
What do you mean?
So the LongCoT models trained up to, say, 24K tokens basically hit a wall. If you tried to make them reason for much longer at test time, their performance just plateaued. They didn't get better.
Okay, that makes sense. They weren't trained for longer contexts.
But the Delethink models, they just kept going. Even though they were only ever trained seeing 8K chunks, when given a bigger token budget at test time, their accuracy continued to improve well beyond that 24K training limit.
Seriously? So they could generalize their reasoning ability to much longer sequences?
Yeah, they showed it scaling effectively to over 100,000 tokens. They pushed the 1.5b model to a 96K token budget on AIM-24, reaching 39% accuracy, with the average solution length being around 36K tokens.
That really proves the concept. It enables reasoning at a scale that was just computationally impossible before.
Definitely.
But hang on, learning to write that perfect little carryover state, that summary, that seems incredibly hard. Isn't that just shifting the difficulty? Do the models have to learn this totally from scratch during the RL phase?
That's maybe the most surprising finding. You think so, right? RL works best when it starts with a reasonable policy. So the researchers checked. They took a bunch of existing pre-trained models, R1 Distill, but also bigger ones like GPT-OSS 120b, Quinn 330b, and they just ran the Delethink mechanism on them. Zero shot. No RL training for this specific summarization task yet.
And what happened?
Astoundingly, the models already produced pretty good Markovian traces. Straight out of the box, using Delethink's reset and carryover process, they often got most, sometimes even all, of the performance they'd get with standard LongCoT, where they see the full history.
No way! So the ability to kind of condense the important stuff into recent context is already latent in these big pre-trained models.
It seems so. Which is fantastic news for Delethink, because it means RL isn't starting from zero trying to learn this incredibly difficult summarization skill. It's starting with a policy that already mostly does the right thing. It just needs refinement.
That explains why the RL works so well in scales. It's optimizing an inherent capability.
Exactly. And they even pushed it. They tried it on tasks specifically designed to break this kind of approach, like crossword bench, where you really need to remember things from way back.
Right, deleting context there should be fatal.
You'd think.
Yeah.
But even there, the Delethink-style models held up surprisingly well, performing competitively. It suggests this ability to write a useful carryover state is pretty robust.
So stepping back, the big takeaway is that rethinking the environment is a super powerful way to make progress. Instead of just throwing more hardware at the quadratic problem,
you change the rules of the game with a software constraint, forcing the model into a more efficient mode of operation.
And this has wider implications, doesn't it, for future model architectures?
Oh, absolutely. The fact that Delethink works, that complex reasoning can apparently be done effectively in this Markovian fixed state way, that's huge.
Why huge?
Because there's a whole class of sequence model architectures out there, things like state space models, Mamba is a popular one right now, or models using linear attention or sparse attention. Their main selling point is that they don't have quadratic scaling. They process sequences linearly or near linearly, often using a fixed size state.
So if reasoning can be done Markovian, as Delethink shows,
then these inherently non-quadratic architectures might be a perfect match for building the next generation of super efficient, long-horizon reasoning systems. It lends strong evidence to support exploring those architectures more.
that really could shift how people design foundation models going forward.
It could.
Okay, final thought then, something to chew on. The paper floats a couple of ideas about why these pre-trained models seem to have this latent Markovian ability already. Is it deep? Like, maybe human thinking is also sort of Markovian. We don't keep the entire chain of logic perfectly in mind, just the key conclusions needed for the next step.
That's one possibility. Or maybe it's more mundane.
Like what?
Like maybe it's just an artifact of pre-training. Most models are pre-trained on data chopped into fixed context windows, often around 8K tokens. So maybe they've implicitly learned to think efficiently and summarize within those bounds simply because that's the data they always saw.
Interesting. So an emergent property of the training setup.
Could be. Either way, Delethink proves that decoupling thinking length from context size works, and works well. So maybe the question for you listening is, how might this principle, this environmental redesign, change how we build and train LLMs for complex tasks in the future? Is constant context the way forward?
Definitely food for thought. If you want to get your hands dirty with the details, the code and model weights are open source. You can find them on Hugging Face and GitHub under McGill, NLP, the Markovian Thinker. We'll link it.
That's all for this deep dive with AI Paper Podcasts. Thanks for tuning in.
See you next time.